So we want to do the electron dot diagram of P2S, and they tell me that the P's in the middle. Okay. Although, you can make an argument either way, because S can make 2 bonds, so it could be in the middle, but P can make 3 bonds. So it's probably better in the middle. Okay. So, oops, I don't want to do that. I just had it on pen. Why did you not turn pen in color? Okay, so I can't picture how this goes together, so I'm going to do the math. Okay, I've got 2 P's and 1 S. I'd worry about the happy number. The happy number for phosphorus, the 2 phosphoruses, each one's happy with 8, so that's going to be a total of 16. The sulfur's happy with 8. So 16 and 8 is 24. You do a lot of math with 8s in this one. Okay. The phosphorus is in group 5A, so it has 5. And there's 2 of them. So that's 10. And the sulfur is in group 6, so it has 6. So 10 and 6 is 16. 24 minus 16 is 8, divided by 2 is 4. Everybody okay with that? Yeah. No, it's S2P. That's, that one of those 2 P's is central. Okay, sorry for the confusion. And I would write it as P3. I wouldn't write that separate P off separate. I should put a comma there. Sorry, Miss Spencer, my 6th grade English teacher, who taught me about clauses and how to isolate them with commas. She got her clauses into me. Okay, so I know that this is the order, and I know the fewest I can get away with is 2 bonds. But my math says I have to put in 4 bonds. Okay? So I got to put in 2 more. And I actually have 3 choices about where they go. I can make it 2 double bonds, or I can make it a single bond and a triple bond, or I could make it a triple bond and a single bond. See, I could, in putting 2 extra, there's 3 ways I could do it. I could put them both between the phosphorus, both between the phosphorus and the sulfur, or 1 on each side. Turns out, one of these won't happen. Well, you got to fill the rest of them up. So I need 4 more electrons on that phosphorus and 4 more on that sulfur. I've got 16 electrons there because I got 8 here and 8 there. That's 16. Right? On this phosphorus, I have to put 3 more pair. And need another pair there. That gives me 8 over here and 8 over there. There's my 16. This phosphorus needs 1 pair, and this sulfur, down here, needs 3 pair. And that gives me my 16. So I've got the right number of bonds. I got the right number. But what I don't have is I don't have the right number of bonds. Because phosphorus always wants to make 3 bonds. Sulfur always wants to make 2 bonds. So if you look at the 3 of these, the middle one never makes the right number of bonds. Right? Phosphorus always makes 4 bonds. That one in the middle is not happy. Okay? But it's the only way it's going to fit together. But if you look at this one, the sulfur's made 2 bonds. Right? So the sulfur, at least the sulfur's happy. The phosphorus is only made, the other phosphorus is only made 2, it's not happy, but at least the sulfur's happy on this one, right? On this one, the phosphorus has made 3 bonds. So that phosphorus is happy. None of the other 2 are, because the phosphorus in the middle is made 4 and the sulfur's only made 1. But at least the one on the end's happy. If we look at the last one, the phosphorus in the middle isn't happy because it's got 4. The sulfur's got 3, so it's not happy. The phosphorus only got 1, so it's not happy. None of them have the right number of bonds. So this one doesn't form. The other two do. Because I got to weigh at least one of them gets the right number of bonds. Because here, the sulfur has the right number of bonds. Here, the phosphorus has the right number of bonds. And this one, neither of them, none of them had the right number of bonds. This sulfur had 3. Sulfur doesn't want 3. Phosphorus, this phosphorus had 4. Doesn't want 4. This phosphorus had only 1. And it wants 3. So it had none that were the right size. Does that make sense? And see how that math made it easy for me to decide that I had double bonds and had choices about where to put them? Because this is the same problem as the one when you did N2O. And we struggled trying to follow all the dots on N2O. Yeah, Ali.
How do you know phosphorus wants 3?
Because it's in group 5A. And 3 more would make it look like a noble gas. So we're still using that noble gas configuration stuff. We learned all that for that purpose. Okay? So they want to fill up that orbital. They're going to do it by sharing. Okay? So we struggled trying to explain N2O, trying to follow each one of those individual dots, right? And we came up with 2 doubles and a triple when we followed all the dots, right? Well, this way was a lot faster to get to 2 doubles and a triple. 2 doubles or a triple. I think so. All right. Now start to be lazier. Another way of indicating bonds. Right now, these 2 pair of electrons in between indicate a bond. Sometimes we replace those with lines. Anybody surprised by that? That a line could take the place of 2 dots, connecting the 2 pieces? I like the fact that it shows the bond nature a little bit better. It says these 2 pieces are connected to each other. Okay? Now, when you do that, you can't call this an electron dot diagram. Because it's not. Not everything's a dot. So you call it a structural formula. Now, only thing we got to be careful of is we got to remember that when we count, a line counts as 2. You can only use lines for bonds. You can't use them for these ones that aren't bonded. You can't use them for those lone pair, I think they called it in the reading guide. Okay. So if I look at this water molecule, the hydrogen has 2 electrons next to it because that bond is 2 electrons. The other hydrogen has 2 electrons next to it because that bond is 2 electrons. And the oxygen has 8. 1 pair, 2 pair, 3 pair, 4 pair. Okay. I mean, so a triple bond would look like this. Three lines is a triple bond. So if I count, this is, it's bizarre. 2, 4, 6, 8 electrons on nitrogen. Bizarre. I have another one here someplace. Right down the bottom, a double bond. Double bond, it's 2 lines. So if I look at this oxygen, it's got 2, 4, 6, 8 electrons around it. The carbon has 2, 4, 6, 8 electrons around it. So that's all we have to do is count lines as 2. Big deal? Okay. So, we had some electrons bouncing around all over the place when we tried to build these things. And that's because we skipped one of the possibilities about moving electrons around, and that is a coordinate covalent bond. Okay, and a coordinate covalent bond is where one atom gives not just one electron to the bond, it gives both electrons to the bond. Sorry. Okay. All right, so for example, one of the ones we struggled with trying to draw on yesterday's homework was carbon monoxide, CO. So doing it the old-fashioned way, I put C with its 4 dots next to O with its 6 dots. And I'm color coding mine so you see where they come from. You really can't tell, but I color code mine so the ones that belong to C are white, the ones that belong to O when we started are yellow. Is anybody happy there? No. So we have to share more electrons. So I take one from carbon and one from oxygen, erase them, and put them in there, and make my double bond. Okay. Now, any atom happy there? The oxygen's happy. The oxygen has 8 valence electrons around it, but the carbon only has 6. So somehow, we have to get 2 more electrons onto oxygen without losing any from carbon. So it has to be someplace where carbon and oxygen can both count them. And that's in the bond. So that whole pair on top goes into the bond. Okay? So I make a triple bond. But that's going to give me 3 bonds, so I pair these up, because we always have 4 pairs of electrons. And since I color-coded them, you can tell that more of them came from oxygen than from carbon. Now, you can't tell when you do the math. Okay? I just want to let you know it's a possibility, that this is one of the ways they form. Because we had trouble building things because we were trying to move one electron at a time. It turns out sometimes you have to move a whole pair. It is not our first choice. It is our last choice. Okay? We won't be able to tell for sure if we do the math. But if we did the math for this, we'd come up with a triple bond. Because happy is 8 and 8, 16. Have is 4 plus 6, 10. 16 minus 10 is 6. Divide by 2, 3. CO has 3 bonds. Okay. Now, what they do to indicate it with the lines is they turn one of the lines into an arrow. Okay? And this arrow is pointing from the oxygen to the carbon because the oxygen donated the whole pair. That whole pair of electrons came from oxygen. That's why the arrow goes from the oxygen to the carbon. So how do you know if there is a coordinate covalent bond? How do you know? How do you know? Well, the ultimate answer is You got to draw it the way I did the first time and move the electrons around and see what happened. Okay, we're gonna introduce this concept called polyatomic ions real soon, like next slide. But it happens often in those. You'll see them in just a few minutes. But one of the clues is, if an element has the wrong number of bonds, this is one of the ways that can happen. Because if you look at CO, carbon wants to make 4 bonds, but in CO it's only made 3. Oxygen wants to make 2 bonds, but in CO it's made 3. We got things with the wrong number of bonds. That's a clue that there's probably a coordinate covalent bond in there someplace. Okay? So if you have one where something, when you build it, you've got to have the wrong number of bonds, then you know you probably have a coordinate covalent bond in there someplace. Just double check. Okay. So I just doubted myself, and I shouldn't. No. Okay. So, polyatomic ions. Okay. So let's take this word apart. Prefix poly. What is many atomic atoms. So many atom ion. So all the ions we've seen, we've taken as just a single element off the periodic table, right? There are groups of atoms that when you put them together, they have a charge. That in putting those atoms together, you either have to put in some extra electrons or take out some electrons. So they're going to be a group of atoms with a charge, something like, oops, CO3 with a 2 negative charge. That is a many-atomed, because you got 1 carbon and 4 oxygens, but it's not a molecule because it's got a charge. Okay? Now, what's holding CO3 2 minus together is covalent bonds. But in order to make those covalent bonds, you had to throw 2 extra electrons in. That's what the 2 minus means. That there's 2 extra electrons someplace in those 4 atoms. You don't know exactly where in those 4 atoms it is. And since you don't know where they put the extra 2 electrons, you can't build it by putting dots in, because you don't know where the dots go. So if you're going to do if you're going to build the structures for polyatomic ions, you have to do the math. There is no way around it. There's going to be one slight difference. We're still going to talk about how many they have how many to make them happy. That's not going to change. But what's going to change is how many they have. Because I get the have number by looking it up on the periodic table, but then I got to take into account the charge, because they have a charge. So the have number is going to be different. CO3 2 minus has a negative charge of 2. How do you get a 2 negative charge? You add 2 electrons, right? So if it's negative, I have to add extra electrons. So the fact they told me it was 2 negative is, for that, I would do all this math for have, and then I'd have to add plus 2 because it's got a charge. It's got 2 extra electrons. I apologize for the things we have extra as negative. I didn't get to pick what positive and what was negative. We can blame Ben Franklin for that one. He picked the wrong one to be positive. Made our life difficult. If it's positive, the way you make a positive ion is you lose electrons. Right? So if I got a positive 2 charge, a 2 positive charge, I must have lost somewhere, those atoms in this thing must have lost 2 electrons to something else. Since we can't say specifically which atom lost or gained those electrons, we can't put the negative sign or the positive sign right next to an atom, because that would say it's that one. So instead, we have to surround it in brackets and write the charge outside. It says somewhere in here, there are 2 extra electrons. I don't know which ones they are. So that's the brackets say. The brackets say, this has a charge, and I write the charge outside. It says something in those brackets, somewhere in there, there's a couple extra electrons, or there's an electron missing in here someplace. So let's try a couple and see what it's like. Okay. One of the polyatomic ions is NH4+. It's called ammonium. Okay. Ammonium, since it has the charge, means I lost an electron, but did I lose off nitrogen or hydrogen? Can you tell? Now you can't tell which one lost it. So since we don't know where to take the dot off of, we have to do the math. I can't just start by drawing dots because I don't know where to take the dot off. So I'm going to do the math. I got to worry about a happy number and a have number. I have to worry about nitrogen and 4 hydrogens. Happy number for nitrogen is 8. Happy number for hydrogen is 2, but there's 4 of them. So I have 8 more. 8 and 8 is 16. Happy number is always going to be 8 or 2. Have number. Nitrogen has 5. Hydrogen has 1, but there's 4 of them. And usually we add these up right now. But if I add these up and got 9, we'd have a real problem. What would be the real problem with 9?
Because 9 minus 6 is not an even number.
It's got to be.
Not even numbers.
Yeah, we can't do half a bond, right? So it's got to be an even number, but we're lucky because it's got this plus sign. What is it? How do you make something a positive ion? You lose an electron, right? So I lose an electron. Subtract 1 because of the charge. Make sense? So this is now going to have 8. 16 minus 8 is 8. Divided by 2 is 4. So this has 4 bonds. I go back to my original formula and say there are 5 atoms in that. What are the fewest number of bonds I could get away with 5 atoms? 4.
Wait, so if it's a plus though, it doesn't mean that has one less electron?
That's why, so it has 1 less. That's why I subtracted 1.
Oh, okay.
No, I went right with your words. Has 1 less, so I subtract 1. Okay? So 4 bonds, and the fewest I could get away with would be 4, right? Right? 5 atoms, 4 is the fewest. So I put in 4. They're all single bonds. Ooh, and now I can do it with lines. All right. Whew. Okay? And then I make sure, then I fill up everything to look like a noble gas. Well, that's pretty easy on this one, right? Because the nitrogen's got 8. 4 lines is 8. Hydrogen, you should always have just one line coming out of a hydrogen, because that's 2 electrons, right? So that's what it's like. I lost an electron. Where? Can you tell? Since you can't tell where the lost electron is, you can't put a plus sign right here because it would say that hydrogen, right? So that's why we do the brackets and say this has a plus sign. It says somewhere in there we've lost an electron. We can't tell you exactly where we lost it. Yeah. It's not so much that we can't tell, we don't care. It really is what it comes down to. We don't care. Okay, it doesn't really make a difference. So there's no reason to look to see which one. Because electron's an electron. Doesn't matter where it came from. Doesn't matter where it's going. It's an electron. It doesn't have a future. Doesn't have a past. It has an existence. Okay. Oops, we just did that one. Oops. That's not supposed to be. That's supposed to be SO3. Why does that not say SO3 2 minus? Like it's supposed to. No, literally, it says supposed to. Okay. SO3 2 minus. So doing the math, I've got an S, 3 O's, and a 2 minus charge. Right? Happy. The S is happy with 8. The O is happy with 8. There are 3 O's, so I have to multiply that by 3. Now, to me, that looks like I have 4 8s. 4 8s is 32. I think multiplying by 4 is easier than multiplying by 3 and adding. Okay. Half number. S has 6. O has 6. There are 3 of them. That's 18. Okay. That takes care of the atoms, but now I've got to deal with the charge. This has a charge of 2 negative. How do you get a charge of 2 negative? You gain 2 negative pieces, right? So I have to add 2 more for the charge. So that gives me 26. 32 minus 26 is 6, divided by 2 is 3. So this has 3 bonds. There are 4 atoms. What's the fewest number of bonds you can get away with? 18 plus 6 is 24, and 2 more is 26. Okay. So we have an S. And just for you getting used to it, if we do not have long chains of molecules. If you see something and then O, all those O's are hooked to that thing. So you see SO3, all 3 O's are going to be hooked to the S. See ClO3, all 3 O's are hooked to that Cl. Okay. But, there's my 3 bonds, and then fill everything up and put a 2 minus on the outside. With a 2 negative charge. So that would be my, oops, there's no dot there. That would be my answer. Have a pleasant afternoon.